Hello, everyone, and welcome to today's webinar, The Effectiveness of Ammonium Sulfate versus New Granular Sulfur Fertilizers and Crop Production. This is brought to you by AdvanSix, a leading manufacturer of ammonium sulfate fertilizer. I'm Robin Sitberg of Meister Media Worldwide, publisher of CropLife magazine, and thank you so much for joining us today. In this webinar, our speaker, the distinguished Dr. S.H. Norman Chain, will review available data on the efficacy of granular elemental sulfur fertilizers, whether granulated with bentonite or phosphate products. Research is showing that these products confer little or limited plant-available sulfate sulfur within the season of application. Dr. Chain will discuss a more effective way to meet late-season sulfur needs of modern corn hybrids and soybean varieties. In addition, this webinar has been approved for 1 CEU credit from CCA. We'll submit the database of the webinar attendees afterwards, and credits will be posted to each attendee's CCA account. We will have some time for questions and answers after the presentation, so if at any time during your presentation you'd like to ask a question, type it in the question pane at the lower left panel of your presentation window and click Submit. We'll do our best to answer as many questions as we can at the end. We're really fortunate to have quite an accomplished speaker today, and I'd like to take a moment to introduce him. Dr. S.H. Norman Chain is world-renowned for his research and discoveries in the area of phosphate rock, as well as for his work on various other fertilizers, including sulfur products and their availability to crops. Awarded the inaugural Pierre Becker Award in London for his fertilizer research, Dr. Chain has published more than 135 papers, consulted for various United Nations agencies, and advised companies and scientists around the globe. So with that, I'd like to turn the program over to Dr. Chain.
Thank you, Robin, for the introduction. Good afternoon, ladies and gentlemen. Thank you for taking your time to attend this presentation on the website. Some of you may have heard the subject matters at the annual Agronomic Society's meeting. During the past several years, I have presented the subject matters, the topics, several times. But some of you may have not heard the topics. If so, I hope that you will learn something new after the presentation. As you can see the title, we're going to talk about the agronomic effectiveness of traditional sulfur fertilizers such as ammonium sulfate compared to some new sulfur fertilizers. Some of you may not be aware of those new sulfur fertilizers in crop production. Now, sulfur nutrient is very, very important. It's an essential nutrient for crop growth. Although sulfur is considered the secondary nutrient, it doesn't mean that it is the secondary essential nutrient. It is one of the essential nutrients. The reason why it's called secondary is because the amount of sulfur nutrient required by the crops is after NPK. So these three are the so-called major nutrients, and sulfur is considered as a secondary. But keep in mind, it does not mean it is secondary essential. It is still essential. The reason called secondary is because the amount of sulfur nutrient required is secondary, not as big, as huge as NPK. Soil sulfur deficiency has become a major problem for crop production in many countries due to the extensive and popular use of high analysis nitrogen and phosphorus fertilizers such as urea, MAP, that's monoammonium phosphate, DAP, diammonium phosphate, and TSP, triple superphosphate. Those popular fertilizers, they contain very little or almost no sulfur nutrient. So continuously to apply this MAP, DAP, TSP, urea, and so on, that soil do not receive the fertilizer from this fertilizer without sulfur. The other one is the sulfur deficiency has become a problem is because the reduction in SO2 emission from industry. Normally, it's the coal burning power plants. they burn the coal and then emit the SO2 gas into the air. Now, to the atmosphere, as required by the environmental laws, that's the law require the SO2 emission be cut down, curtailed, so that a significant local effect on reducing sulfur deposition from the air to the soil contributes another reason for soil becomes more and more sulfur deficiencies. This slide shows the sulfur wet deposition from air or from atmospheres. This is because the decrease in SO2 emission to the atmosphere has resulted in the decrease in atmosphere sulfur, SO4S. Now, this chemical reaction shows the SO2 in the air with water and oxygen. Then you got the sulfuric acid deposition from the air to the soil or to the farm lands. The figure, the map shows that along the history, if you look at the 1985, reddish color, the very reddish color represents the amount of sulfur deposition from air to the land. Now, this is 24 kilo on the left side, lower corner of the left side. You have this reddish color represents more than 24 kilo per hectare of SO4. So if you convert this to sulfur, S only, you need to divide by 3. So that means the reddish color is greater than 8 kilo sulfur per hectare, okay? Not 24. 24 is SO4. So divide by 3, that will be 8. Now you look at the map of the United States back in 1985, you see that in the eastern part, almost half of the United States, they are very, very reddish, indicate there's a lot of sulfur deposition from the air to the land, to the farmlands back in 1985. And then you look at 1990, 5 years later, still quite reddish in the eastern part of the United States map. Then 1995, the environmental law began to kick in, and then you see that a reduction in sulfur deposition in the same regions in 1995. Then you see the year 2000, it's less and less. Then to 2005, still some states enriched with the deposition of sulfur. Now to 2010, almost all the eastern part, the reddish color almost disappeared, and then 2014, basically the SO2 emissions was under well control, and therefore no more free sulfur nutrient from the air to the land, and so the farmlands will begin to show up the sulfur deficiency. This slide shows the symptoms of sulfur deficiency on corn. On the left side, you see this is the young corn plant sulfur deficiency is typical symptoms, yellow colors of the corn leaves. On the right, after application of ammonium sulfate provided sulfur, you see the corn leaves kind of greenish. So basically, the plant sulfur deficiency shows the yellow color for corn, and this is the same as nitrogen. Nitrogen also, without adequate nitrogen, the corn plant will show, or most of the plant will show, yellowish color. The differences between nitrogen deficiency and sulfur deficiency is very obvious as such, because sulfur is less mobile in the plant tissues. So normally, as a plant or corn is growing, you see these older leaves still maintain a bit of greenish color, and the young leaves of corn will become more yellowish. That's because the sulfur is less mobile to translocate the sulfur from the older leaves to the younger leaves. On the other hand, for nitrogen is mobile. So when the younger leaves needs nitrogen, the nitrogen from the older leaves then will be translocated, immobilized to the younger leaves. So consequently, you see the younger leaves are yellow, all the leaves kind of greener, that's the sulfur deficiency. On the other hand, if the younger leaves are kind of greenish and the older leaves kind of yellowish, that suggests this nitrogen deficiency. Okay? Now, this slide shows the field trial of soybean with soybeans. And on the left, you see the soybean is the TSP, that triple superphosphate, almost no sulfur there. On the right side is a single superphosphate. Now, single superphosphate has the phosphorus, but also has a gypsum. So gypsum provides sulfur. On the lower side, you see the TSP provides 0 kilo per hectare of sulfur. On the right side, when SSP applied at 70 kilo, same rate as TSP, it provides 36 kilo sulfur per hectare. So basically, SSP had sulfur. TSP does not have sulfur. This picture was taken in the country of Brazil, called Mato Grosso state. So obviously, you see the TSP shows yellowish color of soybean, whereas the single superphosphate is greener, mainly because of sulfur deficiency symptoms in the TSP treatment. Now, different forms of sulfur nutrient in different fertilizers, okay? Basically, we can classify as such. One is the so-called water-soluble sulfate sulfur, SO4S. And this type of form, it provides readily quickly available sulfur, such as ammonium sulfate, as is well known. Now, sulfate sulfur, because it is water-soluble, so it is susceptible to the leaching when rainfall has become severe, especially in the coarse texture. That is the sandy soil, for example. Now, under rainfall, you may have leaching of sulfate sulfur. How about the gypsum? Gypsum is slightly water-soluble. It also has a SO4S, sulfate sulfur. It's normally plant available if the gypsum is applied in a powder form. Moderately plant available if the gypsum is applied in the pellets. Pelletized gypsum, because large pellet size, and also depends on the hardness of the granules or pellets. So it's less soluble, less available than powder, but more work is needed to compare the two, powder versus pellets of gypsum. Now, gypsum is commonly used as a soil amendment rather than as a fertilizer, because it's normally applied at a very high rate, can be up to 3 to 4 tons per hectare, to improve the soil structure of alkaline clay soils. In other words, that this type of soil, clay soils, normally the water filtration is limited, and the soil structure is kind of form the aggregate difficult for good structure. So gypsum has been used to improve the soil structure, facilitate the water filtration rate, and so on. So it's normally used as soil amendment rather than as fertilizers. The gypsum also subject to leaching, except it is less susceptible than water-soluble ammonium sulfate. The other one is the elemental sulfur. This is called ES, the elemental sulfur. Basically, it's the 100% sulfur. Elemental sulfur is not plant available. In other words, the plant cannot take up ES as a sulfur nutrient. The ES must be biologically oxidized to SO4, such as water-soluble SO4, in the soil, so the plant roots can take up the SO4, not ES, elemental sulfur. The oxidation rate of sulfur depends on the forms. For example, powdered element sulfur, then its oxidation is faster. If you apply the granular elemental sulfur, the oxidation will be a little bit slower, and we'll discuss more detail on these topics, the granular elemental sulfur oxidation things. The element sulfur, because it's water insoluble and in pure elemental sulfur form, so it is not subject to leaching in the soil. However, if the element sulfur is oxidized to sulfate sulfur, then it is subject to leaching after it is once it is oxidized to sulfate sulfur. This table shows some commercial products of granular sulfur fertilizer. The products kind of new, and these are the commercial grade. Please remember they are all in granular form, not powder form, granular form. And couple examples in here. For example, you have Micro Essentials, and the brand name is Micro Essential. It is MES. MES stands for Micro Essential. 10S means it has 10% of total sulfur. The chemical composition is MAP, ammonium phosphate plus elemental sulfur plus ammonium sulfate. The composition of the two forms of sulfur, such elemental sulfur has 5%, and then ammonium sulfate is another 5%. So total is 10%, and the ratio between the elemental sulfur and ammonium sulfur is 50-50 or 1-to-1. The other product also Micro Essential. So MES 15, and the 15% is total sulfur. The elemental sulfur 7.5, ammonium sulfate is another 7.5. So again, these two products normally is a 50-50 ratio between elemental sulfur and ammonium sulfate. These Micro Essential products are being marketed by a company called Mosaic. You probably have heard about that. The other type of product is called Grow. This is the brand names products mainly marketed by another company called Shell Solution company. The company produces two types of product. One is the TSP with 12% of sulfur, and the composition is TSP plus elemental sulfur, no ammonium sulfate. So the 12% of total sulfur as 12% of elemental sulfur and 0% of ammonium sulfate. Okay, ammonium sulfate sulfur. The other product is the same, TSP12S, but this one has a mixture of elemental sulfur and ammonium sulfate. Again, total 12%. The difference is that this one has the elemental sulfur on 8%, and the 4% is ammonium sulfate sulfur. So the two products, basically, total sulfur is the same, but the composition are not the same. One is 100% elemental sulfur. The other one is the mixture of elemental sulfur plus ammonium sulfate sulfur. The other two products on the table is the Tiger Soft company. This Tiger 90 CR basically is the old name called Tiger 90, which is well known. Now they changed the name to CR, same Tiger 90. It's a control release. That's what's called CR. And the fertilizer basically is a bentonite, granulated elemental sulfur, with a total sulfur. It's 90% with elemental sulfur and no ammonium sulfate. So that's what's called Tiger 90. So that means the bentonite has about 10% and elemental sulfur 90%. The other product is called Tiger XP. This one is, again, the bentonite ES, except the difference is the total S is only 85%, and elemental sulfur is 85%, and 10% of bentonite, and then plus 5%, the so-called activators. The company claimed this activator, 5%, can activate the sulfur oxidation, elemental sulfur oxidation. So basically, this represents certain products of in the market. Now, the producers' claim of those products, granular elemental sulfur with or without ammonium sulfate, plus minus AS, after application, within the seasons of application, the producer they have claimed that if you only the elemental sulfur only in bentonite or TSP, the oxidation of elemental sulfur to sulfate sulfur provides the available sulfur during the crop growth to maturity. Within the seasons of crop growth, the elemental sulfur provides all the available sulfur. For the other products, such as a mixture of ES plus ammonium sulfate product, with MAP, DAP, or TSP. The producer are claiming that ammonium sulfate, which is water soluble, provides available sulfur during the early crop growth, okay? While ES oxidation provides available sulfur later on during the crop growth to maturity. In other words, the early available sulfur comes from ammonium sulfate. Later available sulfur comes from ammonium sulfur oxidation within the seasons of application. So we are going to examine that whether these claims are really representative of the product's effectiveness. Let's take a quick look at the sulfur oxidation. This slide shows if we incorporate the powdered element sulfur, such as distribution of dots, represents the powdered element sulfur, oxidation will be fast because it's very fine particle size and incorporate in the soil. Now, if we incorporate the granular element sulfur, same thing you see here, then this granule, will be dissolved and disintegrate because water soluble, MAP, DAP, TSP, but the released powdered element sulfur will be clustered, localized at the granule size because they are just elemental sulfur particles, and unless you disturb or plow the soil, this particle will be localized. And this is localized, I call locality effect. So locality effect here, you can see that is localized. Furthermore, the element sulfur is hydrophobic. That means the water repellent. They have a tendency to, because the water repellent, the element sulfur particle will try to coalesce together to form larger aggregates because disperse from the water. And this will further increase the aggregates, the larger particle size aggregates, and that will further decrease the ES oxidation because the surface area of sulfur oxidation being reduced. Remember, this surface area of powder is very huge because each particle represents a very large surface area where the disintegrate by cluster and sulfur, the surface area will be limited, reduced because they clustered together. Now, for the oxidation, this microorganism must attach to the surface of elemental sulfur. Okay, so if Thiobacillus, the bacteria, cannot attach to the surface of elemental sulfur particles, then oxidation will be reduced or slow down. Give you another example. This slide shows the bentonite granular element sulfur granule applied to the soil surface after 90 days. On the right side of this granule is a fresh granule of Tiger 90. Basically, it's granulated bentonite with elemental sulfur. Now, that's the fresh one. 90 days after application, you see the left side. This granule has been disintegrated, but it's not totally collapsed. It's still half, of the granules still remain. Means disintegration after 90 days. Still, you could see this partially disintegrated granule left on the soil surface. Now, if the granules disintegrate, you still will see after 90 days or longer, you see that the elemental sulfur particle, the granule disintegrate. This is a Tiger 90 again, but the particles are clustered on the together. You see, and this would reduce tremendously of the sulfur oxidation because you are not disperse the granules unless you plow the soil or disperse the soil ES particles. Otherwise, oxidation will be very, very, very slow. This soil study incubation done by Auburn University here on the Tiger XP, which is the bentonite plus 10% bentonite, 90% element sulfur, and 5% so-called activators. So during the oxidation, up to 10 weeks with the soil, you can see that the granular Tiger XP here, and check that is no sulfur treated, and you see that almost no oxidation at all. But when this bentonite Tiger XP was finally ground to powder, and then through the incubation, you could see the powder, the same material except this was grounded to powder. This remains the same granular form. You can see the powder oxidized much more than granular is almost 0% oxidation. So that tells you that for the sulfur oxidation, the particle size is very, very important. Large granule size such as Tiger 90 will be very, very difficult to be oxidized. How about the MAP? This is 10%, 10S, 5% ammonium sulfur, 5% of ammonium sulfate sulfur. This MAP, the same material is called MES, MES 10S. MAP, MES, because the product normally use the MAP, so it's the same MES 10. And here we could see that the same incubation, so we could see that we apply ammonium sulfate 100 milligram, ES 100 milligrams. In other words, that this product we apply at 200 milligram S per kilo of total sulfur, which has 100 milligram as ammonium sulfate, 100 milligram as elemental sulfur. During the oxidation to 10 weeks, this is the control, almost no oxidation, no so much of sulfate sulfur. The granular form, as I said, that we apply at 100 milligram ammonium sulfate sulfur. After 10 weeks, we recover almost 95, all from 0 time to 10 weeks. Now we apply 100, recover 95. So basically, almost no oxidation. I can see it's a horizontal line. Whereas this product was ground to the powder, in other words, MAP10S, ground to powder form, we could see that the oxidation of elemental sulfur from this applied 100 milligram elemental sulfur here. So the same applies to the granular MES10S or MAP10S marketed by Mosaic companies. Let's see, look at some simple greenhouse experiment with ryegrass, cumulative ryegrass yield. It's after 4 cuts. Then we plot the diameter yield of ryegrass versus the total rate of sulfur applied from these two products. One is was the granular ammonium sulfate. One is the granular MAP10S, which had 5% and 5% of ammonium sulfate, 5% ammonium sulfur. Now, if we look at this AB, this letter indicates when the data point with the same letters, like AA, statistically no significant difference between the two sulfur sources. But in that, say, total sulfur applied 10 milligram per kilo, you could see that ammonium sulfate produce higher significant, statistically significant ryegrass diameter yield than the Mosaic product of this MAP10S, because this is A and this is B. When we apply at 25, then the two are the same, then up to 80 is again the same. Now, this tells us that the sources comparison based on a single rate are not appropriate. It can provide a misleading. For example, if you compare these two products at 25, then you say, oh, these two products were the same. But if you go down to lower rate as 10 milligram, then you can see the ammonium sulfate perform better than the MES10. That's because the oxidation of this MES10 was inadequate to provide available sulfur. So, for example, at a lower rate of 10 milligram, this MAP10S provide only 5 milligram of ammonium sulfate sulfur, versus this one is 10 milligram, and this one has only 5 milligram of ammonium sulfate sulfur. And oxidation of ammonium sulfur is limited, then this would produce or perform better than the other one. So the conclusion here is that at a 10 milligram sulfur, at this rate, the EX oxidation, if any, was not adequate to provide plant available sulfur as like ammonium sulfate. Now, the other one is that done in Brazil is corn, 2 corns. It's a short term, 6 weeks for each. So the data average across the 4 applied sulfur rate is multiple sulfur rates, but we average the rates. And we show in here, this is very important, between the first corn and second corn, there was no mixing. If you mix the soil after first crop, then you disperse, and then mix, and then that would enhance a lot of sulfur oxidation. But under no-till system, normally you don't till or you don't plow the soils. So in this case, we try to mimic the avoiding the disturbance of the soil. So between the first and second crops, no mixing. Okay. So let's look at the data here. You have a control ammonium sulfate, and this is the MES or MAP15S. Now, the first column, we can see the dry matter yield. The control only 7.9, and this is ammonium sulfate 13.3, 11.8 for the dry matter yield, and you see this ABC. So basically, this tells us the ammonium sulfate perform better than MES15S and better than control. This is the sulfur uptake, same ABC. And the second crop, without mixing or dispersing the soil after first corn, the second corn, again, the oxidation of sulfur was limited, and therefore the ammonium sulfate still performed better than MES15S, MES15, and better than control. Sulfur uptake follow the same. So the conclusion is that during 12 weeks of corn growth, without mixing the soil, ES oxidation of MAP15S, if any, was not adequate to provide plant available sulfur as compared with ammonium sulfate. Now, you may ask, how do we know how much of ES oxidation in the mixture of ammonium sulfate and elemental sulfur? So we'll see that this figure simply tells us a simple technique. First, you set up the experiment based on the multiple total sulfur rate from each sulfur source. In this case, we have, say, MAP10S and then ammonium sulfate, two sources. This one has the mixture of 5% ammonium sulfate, 5% element sulfur. Then we measure the sulfur uptake by the crops, and then you apply against the rates of not total but ammonium sulfate. Remember here, ammonium sulfate, not total. How much do we know ammonium sulfate? It simply is the total sulfur applied, multiply the percentage of ammonium sulfate. In this case, we apply, say, total 300 milligram sulfur per kilo of total sulfur, 300 kilo. And then the MAP10S, because of 50-50 of ammonium sulfate and element sulfur. So ammonium sulfate will provide only the 150, because of 50% of total sulfur. Whereas ammonium sulfate, 150 is 150. So the points of MAS, this is ammonium sulfate. So maximum is only up to 150 if you apply 300 milligram sulfur of total sulfur. Then if the results show this kind of trend, say like apply the sulfur rate from 0 to say 200, 350, and then you can see starting here, the sulfur uptake about 5 milligram per part is from the soil, delta S from the soil. For the ammonium sulfate applied at 150, this represents delta S ammonium sulfate, the sulfur uptake from ammonium sulfate. Now, if the MAP10S apply at 150 ammonium sulfate sulfur, or 300 milligram of total sulfur. Now, ammonium sulfate is 150. If the line of MAP10S is above the line of ammonium sulfate, this delta S represents ES, means the sulfur oxidation in the MAP10S contribute available sulfur. So these differences between the MAP10S and AS, ammonium sulfate, represents the contribution of element sulfur oxidation from the MAP10S. And then this ES oxidation can be calculated as delta ES divided by ES applied. In this case, it's 150 also because 50-50 ammonium sulfate and ammonium sulfur ratio. So that will give you the estimation of the degree of elemental sulfur oxidation from the MAP 10S granules. Now, suppose no oxidation at all. In other words, delta S from ES is 0. No delta S from ES oxidation. Then the line of MAP 10S and ammonium sulfate should follow the same line, right? Delta S is 0, so this line should be, dotted line should be the same as in the ammonium sulfate. If this is the case, that suggests that no insignificant sulfur oxidation from the MAP 10S. So this is the techniques to use the estimation of sulfur oxidation. Now let's look at this experiment done in Brazil for wheat grown to maturity. Okay, so we have again two sources: granular ammonium sulfate and then granular MAP 15S. All right, and then we plot the sulfur uptake by wheat total mass at maturity, okay? Unlike corn, it's only 6 weeks, but this is the maturity, versus the rate of ammonium sulfate sulfur applied. Now you see the granular ammonium sulfate and granular MAP 15S, basically the two sources, data points, follow the same single line, 95% significance. So this tells us the results show that the wheat sulfur uptake coming from the ammonium sulfur in granular MAP 15S was nil. In other words, almost none. Otherwise, the data point of granular ammonium MAP 15S, this open circle data point, should be above the line of closed circle point of granular ammonium sulfate. But the results show they follow on the same single line, suggests no significant in sulfur oxidation. The same as in the corn, by 2 crops of corn, you can see that the granular ammonium sulfate and granular MAP 15S, again, the data point follow the same line, suggests that the results show that the sulfur uptake by corn coming from the ammonium sulfur in granular MAP 15S was nil or none or insignificant. Otherwise, the data point should not from two sources should not follow the same single line. Let's briefly talk about the agronomic field trials, okay? There are no results from studies comparing granular ES plus minus ammonium sulfate fertilizer compared to sulfur like ammonium sulfate or gypsum-based product with crop yield data that have been published in peer-reviewed scientific journal. In other words, we have not been able to locate the field trial data published in the standard scientific journals. Despite that many agronomic field trials have been conducted by companies and that the fertilizers in question have been marketed to the farmer for several years. But in the scientific journals, we still have not been able to locate really the scientific data. Most of the agronomic field results have been reported in the literature presented at the conference and published as non-peer-reviewed preceding papers. So what I'm trying to say is that no literature review data could be found from the field trial. And I know in the future there will be more papers to come up, but not as of today, although the product has been marketed for over almost 10 years now. Most field trials also use a single sulfur rate for comparison of different sulfur fertilizer, which may result in a misleading conclusions, as I pointed out. Back to this, let's see. Yeah, as I point out in this slide, you can see that if you use only the single rate as like a 25, then you see two products are equally effective. But if you use the lower rates, it shows the two products are not the same. So therefore, even for field trials, you must conduct the sources comparison based on multiple rates, not just one single rate. It must be multiple rate, so that you will not be misled to the conclusions of the comparison of sources. Let's see. This one is from the conference proceedings, showing a simple one in Brazil for wheat and control. If we took the control as 100% effectiveness, then the gypsum powders about almost 140, 38. And the TSP enriched with 10% of element sulfur. Now you see that 103 and 100, almost no response. So that tells us there was no oxidation of granular TSP with 10% element sulfur to provide available sulfur to wheat, since there was no increase in grain yield as compared to the control, whereas the gypsum in the powder form significantly increased the grain yield of wheat. The other one's the soybean. Here is just very new. This is 2016, just last year's data, by the Purdue University. And here's the grain yield of soybean. No sulfur is 48 bushels per acre. Ammonium sulfate is 60. The MAP10S, this is the Mosaic product, about 55. Okay? So if we calculate the agronomic effectiveness of MAP10S compared to ammonium sulfate, will be 55 minus control 48 divided by ammonium sulfate 60 minus 48. That turned out to 58%. In other words, that the MAP10S was 58% as of ammonium sulfate. Now, if MAP10S had no sulfur oxidation, theoretically, agronomic effectiveness should be 50% because it was 50% of ammonium sulfate in the granules. So the ES of 10S contribute basically only about 8% to the soybean grain yield, and this 8% is almost insignificant. So it shows that inadequate element sulfur oxidation of MAP 10S for soybean in Indiana by Purdue Universities. Now, the other thing is a very important concept of partition of sulfur uptake by modern corn hybrids. This is mainly advocated by Dr. Bellot at the University of Illinois. And what he did was to measure the sulfur uptake along with the corn, in this case corn, high yield modern corn hybrids, along with the stage of corn growth. And as you can see that emphasis on the sulfur accumulation in the grain after R1 and R3, you can see that at the end of maturity, the post-flowering sulfur is a major source of sulfur for grain filling. About 50% of total sulfur uptake by the whole plant in modern corn hybrids, and 50% is very high. His idea is the sulfur requires 50% of sulfur. So after R1 and R3, if the corn cannot get adequate supply of sulfur, then that will reduce the grain yield. So his recommendation is at least top dressing of sulfur after between R1 and R3 may enhance the sulfur uptake and increase the yield. This is some kind of new concept in the high yielding hybrids of corn, and the same as also for sulfur. Now, for soybean, you see that almost 60%, even more total sulfur uptake by soybean seeds or grains, 60%. So it tells you also the importance of sulfur application, top dressing between around about R5, somewhere in here, R5. Then that may increase grain yields of soybean. It's kind of new concept. Unfortunately, I couldn't find the data on this split application of top dressing of sulfur to increase the corn or soybean. Nitrogen has been reported. The top dressing of nitrogen, split application of nitrogen, has been reported by Dr. Bellows. The important things in here. Now, that suggests that the top dressing of sulfur from ammonium sulfate would be pretty good ideas, effective ways to increase the sulfur uptake and therefore increase the grain yields of corn or soybean. And this shows the machine, the spreaders, high-capacity spreader, to top dress the sulfur, ammonium sulfate, somewhere during the midterm after flowering. And it's a good way, and research is needed to get the actual yield data. So in conclusions, that basically we can say that ammonium sulfate component of granular, this new product, ES plus minus ammonium sulfate, is also susceptible to leaching, not just straight ammonium sulfate alone. In other words, when you mix the ammonium sulfate plus ammonium sulfate, this ammonium sulfate component of mosaic product or shell products also subject to leaching because it's the same as ammonium sulfate. Severe ammonium sulfate leaching is also a loss of ammonium sulfate in this product. So if you apply this mosaic product under severe leaching, the ammonium sulfate component will be subject to leaching as well. Now, this ES oxidation will produce the ammonium sulfate sulfur, right? After oxidation, this sulfate sulfur also is subject to leaching under the severe rainfall. Element sulfur is not, but once it is oxidized to sulfate, it can be subject to leaching as well. The agronomic effectiveness of granular ES plus minus AS greatly depends on the rate of ES oxidation, how fast of oxidation, which may be limited by the negative locality effect on the dispersion of element sulfur particle after disintegration of the granules. So that means the residual sulfur from oxidation element sulfur may last second year or third year as well. After tearing, without tearing, will be even slower. The ES oxidation granular product was often found to be not significant to provide available within the seasons of application, despite of claims by their producer. Now, here I underemphasize, within the same seasons of application, I'm not talking about the second year, the third year. It's the first year or the first seasons. We have found that this effectiveness of sulfur oxidation from this granular fertilizer things are not so adequate or significant. The final point is the modern high clearance spreader are effective way to split apply some of nitrogen and sulfur nutrient needed to better satisfy the late season nutritional amount and high yield crops. Now, to split application of nitrogen and sulfur after flowering for corn or soybean, etc., the best way is to use ammonium sulfate, which is easily to be applied and may help. But however, research is needed to get the data. This is just the hypothesis. It's just the proposition. So that's, I think it's more or less concludes my presentation. And thank you very much for your time. I appreciate it. Let's see how much I have used. 48 minutes. Okay, Robin?
Okay, thank you, Dr. Chang. And we do have about 10 minutes left for questions. And we've been receiving some questions already. But if you have a question and you haven't yet submitted it, please type it into the question pane at the bottom left of the control panel and hit send. And like I said, we've gotten a few already. And I'm just going to get started with the first one, which is, what is the recommended time to side dress a corn crop with ammonium sulfate for grain filling? Are you able to address that? Dr. Chang?
Yes.
Oh, are you able to address that first question? What is the
recommended time? I cannot see it all. I don't have the presenter's chart.
No, I'm just reading it to you. So
all right.
You could just go ahead and... So what is the recommended time to side dress a corn crop with ammonium sulfate for grain filling?
Well, it's as you look at slide, let's see, corn, and here is slide 22. Here is the corn. You can see the partition of sulfur uptake by modern corn hybrids. Roughly, you can see that between R1 and R3, but actually can be, depends also on the rainfall after R1 and R3. because if severe rainfall comes, your window of top dressing will be more limited because it's sulfur is subject to leaching even after top dressing. So top dressing, you need to be very important. Look at the weather forecast. Suppose you know the next 1 week that no severe rainfall, then your top dress ammonium sulfate may be okay. So watch out for the weather forecast. If no significant rainfall to come, somewhere between R3 even up to R5, probably still have good timing window to apply top dressing ammonium sulfate. Okay?
Okay, good. Yes, that's good information, and timing seems to be an important topic because our next question also has to do with timing. It's top dressing. When's the best time to top dress ammonium sulfate on soybeans, particularly with soybeans?
It's more or less, let me look at another figure in here. The soybean seems to me can be top dressed at even later days. My figure here shows R5, the sulfur accumulation in soybean grains, more or less after R5, between R5 and R6. So, yeah, the timing are not the same for soybean and corn. Corn will be a little earlier, but soybean seems to me R5, beginning at R5, reproductive stage 5, that the sulfur accumulation in soybean grain begins to accumulate and then last until the maturity. The important is that the sulfur accumulation in soybean grains represent about 60% of total sulfur uptake by soybean, whereas for corn, only about 50%. So the top dressing of ammonium sulfate to provide additional sulfur seems to me even more important for soybean than corn. Of course, both are important, but it seems to me soybean even more critical because a high accumulation of sulfur in the soybean grains. It's okay?
Okay. Yes. Okay, we'll move on to the next question, which is, why don't we ever hear of the locality effect when granular elemental sulfur is applied as an amendment to calcareous soils?
Well, the thing is this granular elemental sulfur, pellets of elemental sulfur, as I mentioned, because of locality effect. So this locality effect means that if you apply the pellets of elemental sulfur, oxidation will be more limited. Now, if you apply the powdered elemental sulfur, so when you say we have not heard about locality effect, most likely people use the powdered elemental sulfur. In the past, when you try to acidify the soil pH, lower the soil pH of the calcareous soil, in the past, normally people apply the powdered elemental sulfur, which is more effective within 1 or 2 years. But nowadays, because you can handle, difficult to handle the powdered elemental sulfur, so we now apply the pellets of powdered of, let's see, are you asking elemental sulfur or gypsum?
Elemental sulfur.
Elemental sulfur, right. So the elemental sulfur in the pellets, such as Tiger product, oxidation will be less. But, yeah, if you apply the pellets of elemental sulfur, there is locality effect and, localized effect, the same as mosaic product or shale product.
Okay. The following question is, would a physical blend of ammonium sulfate and elemental sulfur be able to provide season-long sulfur availability on corn? And the second part is, how about a blend of ammonium sulfate and pelletized gypsum? Do you want me to read that again?
No, I got a question is here. As I mentioned, the mixture of granular elemental sulfur plus ammonium elemental sulfur, that's what you're asking, right, Robin?
I'm sorry.
Mixture
I'm sorry,
of
what was that
ammonium
question?
sulfate plus elemental sulfur, is that right?
Yes.
Okay. Well, the elemental sulfur will be the problem because of the locality effect, right? Now, I'm talking about within the seasons of application. In other words, that the elemental sulfur oxidation is kind of slow in the first crop or first seasons because of the locality effect. But if you wait for the second year and third years, there will be more and more sulfur oxidation. In fact, there's a very new paper just published by Dr. Mike McLaurin in Australia's group, published in the Soil Science Society American Journals, that oxidation rate of mosaic product like MAP10S or 15S, based on their model, they predict that the first year they would expect 40% of element sulfur oxidation, but not 100%. Second year, the residual element sulfur oxidation will be around about 30%. The third year, the residual element sulfur oxidation will be around about 20%. So basically, after 3 years, you probably can expect, based on their model and based on their paper, that 90% of initially applied element sulfur will be recovered or will be available to the crops. Now, this is the theoretical value. I mean, we haven't seen the data yet, but yes, residual effect, like a phosphorus, you have a residual effect from granular element sulfur. But that's the point. The topic we are talking about now, right now, for this presentation, is the first seasons or first crop, nothing to do with residual or the second year crop. Okay? Now, the question about gypsum. Certainly, gypsum is relatively available to the crops, much better than sulfur oxidation. Now, the gypsum will be the availability of gypsum, because now gypsum people use the pellets instead of powder. Okay, pellets, effectiveness of pellets gypsum may depend on the size of gypsum pellets, and most important is depends on the hardness of the pellet of gypsum. When I was in Brazil some years ago, I was told that farmers apply these pellets of gypsum into the sugar canes, and the farmers still could see this pellet gypsum partially decompose or partially dissolve the gypsum after the sugar cane harvest. So that means the pellets, if they are very hard, high in hardness, it's difficult to be broken up, then the gypsum may not be 100% available to the plants. And also it depends on if you incorporate it into the soil or you surface apply. If you surface apply, when it rains, especially severe rainfall, the rainfall may break up the gypsum pellets or even spread or disperse the gypsum granules. And similar to element sulfur granules, normally granular element sulfur should be more effective for pasture than for cereal crops or field crops, because on the pasture, when it rains, it may break up the granule, and then the raindrops may disperse the element sulfur powder. So it's kind of dispersion, disruption, and locality effect will be reduced or minimized as such. So the granular element sulfur probably will be more effective on surface application for pasture. Okay?
Okay. Well, I think that gets us to the limit of our time, but if you did not have a question answered and you submitted one, we do know your email and we can get a hold of you and answer that question after the webinar. So I would just like to remind you that there is an on-demand version of the webinar that will be available within the next 24 hours. And so if you'd like to view all or a portion of this webinar again, just use the same link that you used to see it today. So thank you all for joining us today. Thank you to Dr. Chain and to Advancix for sharing this information with us.